Alright, what's up guys? In this video we're going to pick up with some vector calculus, and we're going to be talking about Green's theorem today. So we have to basically evaluate this line integral, y squared dx minus x squared dy, where c is a positively oriented circle with radius 2 centered at the origin. So there's basically two forms of Green's theorem. There's a circulation form and a flux form. The form that you use to deal with a particular problem will depend on the circumstance. So in this case, we're using the circulation form. So let me just quickly remind you what Green's theorem. It's just the closed line integral f dot dr is equal to our closed line integral p dx plus q dy is equal to the double integral. It would be the partial of q with respect to x minus the partial of p with respect to y dA. Okay? Alright, so that's Green's theorem. The first thing we need to do is identify what p is. So p in this case, if we look at what we have, would just be y cubed, and q in this case will be negative x cubed. So make sure to pay attention to the negative there. So let's go ahead and compute the partial derivatives right quick, and then we'll plug everything in. So we got the partial of q with respect to x. Well, that's just negative 3x squared. Then we'll compute the partial of p with respect to y, and that's basically minus 3y squared. So when we use Green's theorem, we got y cubed dx, sorry, not plus, minus x cubed dy, and so we'll have our double integral. And this would be minus 3x squared minus 3y squared dA. Now, if you notice, it's a positively oriented circle with radius 2 centered at the origin. It's basically a disk. So what we're going to have to do, or what's best to do in this case, is to evaluate this double integral in polar coordinates. And sometimes you will have to change coordinate systems depending on the situations. All integrals, especially double and triple integrals, can't be evaluated using Cartesian coordinate systems. I mean, most triple integrals would be a nightmare to evaluate using Cartesian coordinate systems. That's why for a lot of triple integrals, you convert them into spherical coordinates, because it's easier to deal with integrals that way. So everything can't be evaluated in Cartesian coordinates. So make sure that you're cool with that. So since this would be a very tough integral to do in Cartesian coordinates, well, I don't know if it would be tough to do in Cartesian coordinates, but it's best to do this integral in polar coordinates. So let's convert to polar coordinates here. Now, we know for polar coordinates, let me just quickly remind you that for polar coordinates, remember x is equal to r cosine theta, y is equal to r sine theta, and remember that r squared is equal to x squared plus y squared. And remember that the limit of integration for theta will be from 0 to 2 pi. And the limits of integration for r in this case, since it's a oriented circle with a radius of 2 centered at the origin, well, then that means that the limits for r are going to be from 0 to 2. Okay. And then remember the dA part. A lot of students think that it's dr d theta, but that's not right. Nope. A lot of students think that's right. Make sure that you keep in mind that dA is not r dr d theta. dA is actually r dr d theta. So I just wanted to point that out, because a lot of times students say, oh, dA, that's dr d theta. No, dA is r dr d theta when we're converting it to polar coordinates. So again, this is a disk of radius 2. So that's why I want to do it in polar coordinates. So we'll take our integral y cubed dx minus x cubed dy, and we'll do the integral in polar coordinates. So we have a common -3, so if you actually pull the -3 out, this would be x squared plus y squared dA. Now remember that r times r squared is r cubed, so if we convert this double integral into polar coordinates, which we'll do here on another sheet, we can evaluate it. Okay, so now the integral becomes, I'm going to bring the -3 out front because that's just a constant. And we're evaluating this r dr d theta, so that means that the limits of integration for the outer integral will be from 0 to 2 pi. The limits of integration for the inner integral will be from 0 to 2. And then we'll have r cubed dr d theta in there, because remember that r times r squared is r cubed. And so now we got this integral in polar coordinates, double integral in polar coordinates that we need to deal with. So remember how you deal with double integrals. You integrate with respect to, in this particular case, it will depend on the integral, but you will integrate with respect to r first, treating theta as a constant, and you work your way from the innermost integral to the outermost one, and it works that way for triple integrals too. So hopefully that makes sense. So we'll do that. So we got the integral from 0 to 2, we got r cubed, and remember this is being integrated with respect to r first. So this would be r to the 4th all over 4, evaluated from 0 to 2. 2 to the 3rd is 8, so that means that 2 to the 4th is 16. Divide by 4 will give me 4. Subbing in 0 just gives me a 0, so I'll get 4. So now I got -3 times the integral from 0 to 2 pi, and I'm integrating a constant with respect to theta. Okay, so this becomes -3 times, well, if I'm integrating this constant for respect to theta, this becomes 4 multiplied by theta, evaluated from 0 to 2 pi. So obviously the fundamental theorem of calculus tells us that we plug in this upper limit first, followed by the lower limit after that. So if we sub in the upper limit, which is 2 pi, we'll get 8 pi. If we sub in the 0, we'll get 0. So this would be 8 pi minus 0, which is just 8 pi. We'll then take that constant, -3. It is still a constant, even though it's negative. This will obviously give us -24 pi. Or rather, 8 pi would be -24 pi, which would be our answer. So our final answer for this line integral here, using Green's theorem, y cubed dx plus, not plus, I keep writing plus, it's minus, guys, sorry, x cubed dy. When we use Green's theorem, we get -24 pi using Green's theorem. Sorry for the mistakes with the Sharpie. They've been telling me to stop doing math and pen and Sharpie for years, but I really haven't learned my lesson yet, I guess. So bear with me on the mistakes with the ink. The Sharpie is just more appealing. It appears better on video than a pen, so that's why I do the Sharpie. So I still haven't learned my lesson yet from all these years, but anyway, that is Green's theorem, and that's just another example of us evaluating a line integral using that. Now, as you go further in vector calculus, you'll start learning about things like Stokes' theorem, which is a higher dimensional version of the flux form of Green's theorem. You'll learn about the divergence theorem and all these different kinds of theorems. Vector calculus gets pretty involved. It's a pretty cool class, so I think it's a good class to take. For obviously math majors got to take it, but physics majors should definitely be taking this. You won't like electrodynamics without vector calculus. You won't like it very much, so make sure you're taking vector calculus. All right, guys, I will see y'all next time. Y'all take care.